Today we are going to discuss energy levels in Bohr's atomic model. Bohr gave three postulates of atomic model, and then he obtained an expression for energy of an electron revolving round any nucleus in any stationary orbit. And according to him, energy of an electron in its stationary orbit is equal to minus z square e power 4 m divided by 8 epsilon naught square n square h. And here you can see that everything is a constant. Z is an atomic number, E is charge on an electron, m is equal to mass number of an electron, epsilon naught is absolute permittivity, and h Planck's constants. So when you put the values of all these constants in the expression for energy, the value of energy of an electron revolving in an stationary orbit comes equal to minus 2.18 into 10 to the power minus 18 divided by n square joule. Here n is number of orbits. So if you change the number of orbit, that is also called principal quantum number of orbit, then energy of stationary orbits will be changed as per this formula. And in electron volt, it is minus 13.6 divided by n square. So as per Bohr's energy equation, E is equal to minus 13.6 upon n square. If you put the value of n as 1 for the first orbit, first cell, the energy E1 of an electron in this very cell will be equal to minus 13.6 electron volt. For second cell, if you put n is equal to 2, E2, energy of the electron in second cell, will become equal to minus 3.4 electron volt. Here energy is reduced because with minus sign, if numerical value reduces, it means the value has increased. Now if you take the electron from second cell to third cell, then as per Bohr's energy equation, putting n is equal to 3, energy E3 will become equal to minus 1.5 electron volt. So energy goes on increasing as electron comes towards outer cell. And now when it comes totally outside, energy becomes equal to 0 because the force of attraction is overcome. So on coming outside, when force of attraction becomes 0, then electron comes out from the atom. So the minimum energy required for an electron to come out from its ground state must be equal to plus of this minus 13.6. Therefore, the minimum energy required by an electron to come out from its ground state is equal to plus 13.6 electron volt, and this is called ionization potential. Now in a hydrogen atom, in ground state electron used to be here. Electron used to be in first cell. But after gaining energy it can go to another second cell. After gaining more energy it can go to third cell. So when electron goes from its first cell to second cell, from its ground cell to second cell, then it is called first excited state or second cell. This is your first excited Similarly, when electron goes to third cell, then it is second excited state. Or third cell. And when electron goes in fourth cell, then you can see it is its third excited state, or you can say it fourth cell, fourth orbit or cell, anything you can say, fourth cell. But when you take example of a lithium atom, here 2 electrons are in first cell and 1 electron naturally is there in its second cell. You cannot say that it is in excited state. It is naturally in second cell. This is not its excited state. Here for hydrogen I had said that when an electron is taken, so it in electronic configuration you know that 1s1, this is for hydrogen atom, so it should be there in first cell only. But in case of lithium you find that this is your 1s2 2s1. It is second cell. In lithium the outermost electron naturally is there in its second cell and it is not in excited state. So here you could consider that in hydrogen atom, when electron is taken from its original position of first cell to second cell by giving some energy, then you can say it's first excited state is second cell. But in lithium, this electron is not in excited state. It is naturally there, 2s1. In second cell, 1 electron is there. And this electron is in its ground state, stationary state. Now when energy is given, then it will come to its excited state. But in Bohr's model, we do not think about any element other than hydrogenic elements. We can consider only hydrogen, we can consider singly ionized helium or doubly ionized lithium, so that two of its electrons is taken out and only one electron is left in its first cell. So Bohr's model does not say about any element other than these hydrogenic elements. Line spectra of hydrogen atom can be studied using energy diagram. Here you have energy diagram, and this is your energy axis. It is graduated at equal distances with values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to 14. And with a negative sign, this minus 14 becomes smallest and 0 becomes largest. So when you use the energy equation of Bohr's model of hydrogen atom, E is equal to minus 13.6 divided by n square electron volt. And by replacing n by 1, 2, 3, 4 and so on for different cells, like for first cell, if you put n is equal to 1, then energy comes equal to 13.6 divided by n square. And this is 13.6 with minus sign. Here on this energy axis, you have minus 13 and minus 14. And in between the two, you have minus 13.6. And this you have obtained by replacing n by 1. So this is for first cell. This is your ground state when electron is in first cell. Now when electron goes to second cell, you will replace n by 2, and 2 square means 4. So energy becomes equal to 13.6 divided by 4, and this is your 3.4 with minus sign. And this comes in between minus 3 and minus 4 here somewhere. Here you have a second energy level for the second cell. Now electron revolving in a hydrogen atom cannot have any energies in between the two levels. Electron can have this energy or electron can have this energy. Similarly, if you put n is equal to 3, you have energy 13.6 by 9, and this is equal to 1.5 near about electron volt, and with minus sign. So minus 1.5 comes in between minus 1 and minus 2. Here you have third energy level. Electron can have this energy or this ground state energy. Similarly, when you put n is equal to 4, you have minus 1.8 energy level in electron volt. When you will put n is equal to 5, you have minus 0.54 electron volt energy. But when you reach to 0 energy level, then after, you will not have any discrete energy levels. You have a band of energy. So you find that you have only 5-6 energy levels, discrete energy levels. So it can be explained here. Most of the elements have their outer shell up to 5 or up to 7. At the most they have outermost shell up to 7. So what I mean to say can be understood with the help of an example. Now you have your atomic number for Hg, mercury 80. So when you write the electronic configuration of Hg, it is 1s2, 2s2, 2p6 and it goes up to 6d8. So outermost shell is 6 only. You have such a large atomic number, you can see 80. and you have outermost shell only 6. So all the known elements can have outermost shell up to 6. And most of them have outermost shell up to 5 only. And this is why we have known these series energy labels only 4 5, like Lehman series, Balmer series, Paschen bracket, and one more is known, that is Fun. So when electron jumps from all the excited state to the ground state, you can see from second excited state, first excited state, and this is your second cell, and first excited state. So what is first excited state of an electron in hydrogen atom? In a hydrogen atom, there is only one electron, that is for 1s1, that is for first cell. That is always found in first cell in ground state. In unexcited state, it is in first cell. But if it gets energy from somewhere, when it is highly heated, after gaining energy, the electron may jump from its ground state to first excited state, and it be there. And after some time, when it releases energy in the form of radiation, it again falls back to its ground state. So electron, when reaches to any excited state, as per how much energy it has gained, then it can, after releasing the energy in the form of radiation, it can jump to its ground state. If it relieves the energy, it finally reaches to its ground state. So you can see there is a big difference of energy from even first excited state or second cell to the first cell. And what is energy difference? This is your highest energy minus 3.4 minus lowest. And this is your equal to 10.2 electron volt. This is a large value of energy gap. So if this first energy is provided to an electron in its ground state, you have one electron revolving around nucleus in its ground state, and if this much energy is provided, then it can leave its ground state and it may reach to its first excited state, means second cell. How much energy? 10.2 electron volt. So after gaining 10.2 electron volt, the electron will jump to second cell. Now similarly, if you give energy equal to, let me find the difference of these two, minus 1.5 minus of minus 13.6, then you have energy difference 12.1 electron volt. So if any electron is in ground state here and it has been given energy equal to 12.1 electron volt, then it will reach to its first cell, second cell, and this is your third cell. It will reach to its third cell. Means second excited state. Third cell is its, here you have second cell, first excited state. Third cell is your second excited state. So this is how electrons jump, and this energy gap is very large, and you know that energy is equal to h nu. So when energy is large, so its frequency will be large. This will be for this wavelengths of radiations, these are radiations of wavelengths having large frequency. And you know, when frequency is large, then in EM radiation, it may be UV radiation or X-ray or gamma ray, anything. So this series is called Lyman series, and this is for UV range of EM radiation. Now, when all the electrons, excited electrons, after gaining energy and it has gone to higher levels in the third cell, in the fourth cell, 5 cell, 6 cell or 7 cell. I have drawn up to 7 cell. You can see, because you can write electronic configuration for all the known element up to 7 cell. So why only up to 7 cell we have excitation of energy? Electron can jump up to 7 cell, and it is very excited. It has large value of energy. Now when it leave energy in the form of EM radiation, some EM radiation will come out and the electron will fall back into less excited state or onto ground state. But when it falls on first excited state or second cell, then the energy given will be, here you have energy given in this range, and if you find the wavelength of this wavelength will be in visible range, like 656.3 lambda. This will be the wavelength of this visible range, and this is called Balmer series. This energy difference, which is equal to h nu, and it is in, if you find this value in h nu or hc by lambda, then lambda will come in the visible range, 656.3 wavelength, this much nanometer. Okay, this much your nanometer. So this is the visible range of wavelength. Now it can be seen by human being, and this is your Balmer series. This comes in visible range. You have red color of wavelength, blue, green color of wavelength, one violet color of wavelength. This series only can be seen. The spectrum of this series can be seen. Now you have Paschen infrared region and bracket region. So on second excited state, means on third cell, if an excited electron from fourth cell, fifth cell or sixth cell or seventh cell falls after releasing energy, then the spectrum form is called Paschen series. It falls in infrared region, you cannot see. Similarly, you have bracket series and you have Pfund series. For doing numericals related to Bohr's atomic model, we need to remember some of the formulas, like formula for radius of the circular orbit of an electron, and it is R is equal to epsilon naught n square h square divided by z e square pi m. Here one thing you will notice, that epsilon naught absolute permittivity, Planck's constant h, z, charge on an electron, pi, and mass of an electron, all these things are constant. So you need to remember that R is directly proportional to square of n. And also you can say that if for different atoms, suppose you have hydrogen and then you have helium, lithium, then R is also inversely proportional to Z, atomic number. Similarly, in the equation of energy you can see energy is equal to minus Z square e power 4 m divided by 8 epsilon naught square n square h. So here Charge on an electron is a constant. Mass of an electron is a constant. Absolute permittivity, it is a constant. Planck's constant. So energy is inversely proportional to square of this principal quantum number n. This is the number of cells. So these can be used while doing questions. Now in Rutherford model of an atom, if you have been given question related to Rutherford model, then from this equation, centripetal force is provided by electrostatic force of attraction. You can find that R is inversely proportional to square of V. And when questions are not given related to Rutherford model, then from Bohr's model, second postulate, you can see that mvr is equal to nh by 2 pi, and therefore R is inversely proportional to V only and not the square of V. So keep all these things in mind while doing questions. Here you have question number 1. In the ground state of a hydrogen atom, electron is in its first cell. So radius of Bohr's radius is given by this much. Electron is in its first cell, so you should write R1. R1 is equal to 5.3 into 10 to the power minus 11 meter. The atom is excited such that the radius becomes, now radius has changed. R2 is equal to given your 21.2 into 10 to power minus 11 meter. Now question number 1. Find the value of principal quantum number n. Find the value for this radius. So just we had seen that R is proportional to n square, and this means R1 by R2 is equal to n1 square by n2 square. And therefore, you can find n2 square. Here n is 1, so 1 square into R2 is your 21.2 into 10 to the power minus 11 meter divided by 5.3 into 10 to the power minus 11 meter. All these are cancelled, and therefore n2 can be obtained root under 21.2 by 5.3, and this is your root under 4, and this is your 2. So principal quantum number for that radius given is equal to 2. N is equal to 2, answer. Now question number 2, part 2 of the question. Total energy in this excited state. You can see how energy and principal quantum numbers are related. They are inversely proportional. So since E1 upon, okay, let me write E is inversely proportional to n, square of n, it implies that E1 divided by E2 is equal to n2 square by n1 square, and therefore E2 can be obtained. What is E2? E1 you know, minus 13.6. Energy of ground state, you should remember this. This is equal to minus 13.6 electron volt into n1. n1 is your 1 and n2 is 2, so 2 square, and therefore E2 can be obtained minus 13.6 by 4 electron volt, 3.4. Okay, this is your minus 3.4 electron volt, answer. Now question number 2. The energy level diagram of an element is given in figure. You have energy level diagram for an element. Identify by doing necessary calculations which transition correspond to the emission of a spectral line of wavelength. Okay, out of all these transitions, which is corresponding to this transition of this wavelength? So we have been given energy. So we need to change this wavelength into energy corresponding to this radiation. So what is energy? We know that energy is equal to hc upon lambda. Now, on putting the value of hc and lambda in this equation, h is nearly 6.63 into 10 to the power minus 34, and c, velocity of light, this is your 3 into 10 to the power 8 divided by, here wavelength, it is your 102.7 nanometer. 102.7, and value of h, value of c, all are in SI system. So let us convert nanometer into 10 to the power minus 9 meter. So now everything is in SI system. So we can write the unit of energy as joule. And this is equal to, I have already calculated this, 1.9355 into 10 to the power minus 18 joule. And when it is divided by 1.6 into 10 to the power minus 19, so this will be converted into electron volt. And this has come equal to, energy has come equal to 12.1 electron volt. So now we will find which energy range between the two energy levels is matching 12.1 electron volt. So you can see that this range D transition is matching the same energy range. When you subtract 1.5 from 13.6, you get the same energy range. So transition D is possible in the case of your wavelength 102.7 nanometer. Here transition D is possible as its energy difference is of 12.1 electron volt. So this is your answer. Now let us do the next question. How many spectral lines are there for the transition of an element from fourth energy level, that is also called third excited state, to ground state? So this is your ground state, n is equal to 1, n is equal to 2, this is your first excited state. Cell is 2, excited state is 1. This is cell is 3, excited state is 2. And this is your cell 4, excited state 3rd. Now electron will fall to ground state. Electron will fall to second cell or first excited state from fourth one, and it may fall to third cell. Similarly, from third cell an electron may fall to ground state, or it may fall to second cell. And from second cell also it may fall to ground state. So how many spectral lines? Just count these spectral lines. 1, 2, 3, 4, 5, 6. A total of 6 spectral lines. One more way to do this question is using formula. Number of spectral lines is equal to n into n minus 1 divided by 2. So n given is 4. It's fourth energy level. So do remember, here you have energy level and not the excited state. So this formula is related to energy level. So 4 into 4 minus 1 divided by 2, this is your 4 into 3 by 2, and this also comes 6. So this is how you can solve this kind of